Good evening all, and welcome to this evening's webinar, which is one from Texas Instruments Australia, specifically looking at the revised section of the VCE study design. We're looking at the Maths Methods series here, and the topic for this evening is probability simulations, a topic that I really like myself, and I'm pleased to see it getting additional attention in the revised study design. My name's Brian. I'm your host for this event, and I'll also be speaking first. We have three presenters this evening. I'm going to just do some basic stuff on simulations with dice and coins. I've been with T-Cubed for a while now, one of the founding members of T-Cubed, and possibly because of my age, they've given me the title of mentor, which I quite like. And I also enjoy hosting a lot of our webinar events. Check the webpage to stay up to date for more of them. Now, our second panelist this evening, Frank Moyer. Good evening, Frank.
Good evening, everyone.
Also extensive experience and with a particular interest in rich tasks, investigative approaches to promote deep conceptual learning of mathematics. Now, Frank is going to use our simulations to particularly look at interrogating a classic problem, one that most of you will recognise, and illustrate how quite often an empirical approach or simulated data for an empirical approach can often be more convincing than and readily accessible than the theoretical probability. Look forward to that section. And bringing it all home will be James Mott. James from Southern Cross Grammar School, head of maths there. Good evening, James.
Good evening, everyone.
And James, great to have you on board. We need some young energy in this exercise, so it's great to have you with us. And James is going to be doing taking it yet a step further. He'll be interrogating an actual real data set, particularly looking at the distribution of sample means, which is something specifically referred to in the study design review. Now, I'm going to start by sharing my calculator here. Just a couple of short things here. I've mentioned already this term empirical or theoretical probability, a favourite topic of mine with probability, because I like doing experiments. Quite often, students can have confusion initially in understanding the rules and the formulas of theoretical probability, but can find an easier level of access through an experimental level. Something as simple as rolling dice, tossing coins, or doing a survey, collecting data from an experiment. And I believe they should do all of these things, as well as the electronic simulations, and do that side by side with a study of the theoretical probability. The benefits of experimental probability, as you can see, I've listed there: ease of access. Quite often, students will have greater confidence in results if it's data that they've collected themselves, and very quickly they find that they have a thirst for data. That they realise that in order to increase their level of confidence, they want lots more data. So if they are actually rolling coins and tossing, rolling dice and tossing coins, then they need to speed that up. And here then comes the beauty of simulations, where those physical experiments can be repeated or replaced by an electronic simulation, which can help us get a lot of data very quickly. Now I'm just going to start by adding in a calculator page here, and possibly the simplest that you might start with is a random integer generator for simulating the roll of a single die, a single six-sided cubic die. Can I point out from the start, though, all of the random tools in the software are dependent upon a background algorithm that initially needs to be seeded. If you have a class full of students that have all got brand new calculators straight out of the packet, and then they run a random number generator, well, they'll actually all be starting from the same point in that algorithm, and that won't make it look very random. So what I suggest is run this command. You saw how I accessed it, and ask them to put in any old number. It could be their telephone number, it could be their student ID, just as long as it's different. And when they run that, what's happening now is that next time we access that algorithm, it'll be starting from a different point. Okay, probability menu, you can see where I'm getting that from. Main menu, probability, random. If I select random integer and within there put 1,6, every time I press enter, it's simulating the roll of a regular cubic die. Okay, and one that you might like to, you will probably do this with a junior class. I'm well aware that we're looking at VCE here, but I'm just leading us in through some of these lead up experiments and ideas. You can see what I've done there, and adding randint16 to itself to simulate the roll of 2 dice. And this would be one that you will have done early junior high. What is the probability of each of the possible outcomes there between 2 and 12? And students will have performed this experiment and quickly realize, but hey, I want a lot more data. So rather than do that just a few times as you saw me do, how about we roll the first die 1,000 times and then add that to 1,000 rolls of another die. And there are our results. You could, of course, scroll through those, but I'm going to store them, Control var key for store, and I'm going to call it dice. So that's now a variable, dice. Let's explore that in a, let's see, this time we'll do a data and stats page. So there are our 1,000 results. Click down here to add variable, dice, and there we have it. And as I was expecting, the 7 is the modal group. So this is effectively a dot plot, but because we've got so many values, you're not seeing them as individual dots, and so on. And of course, the least frequent are those 2s, which is a double 1, and the 12, which is a double 6. Another way of showing this is through a spreadsheet. I actually prefer the spreadsheet, where in the first column, I've actually got 1,000 rolls. I've got that randint command 1,000 times, and I've called that die 1. I've done a similar thing in the second column, and in column C, I've created a variable dice. Notice that I've created a new problem here. This is problem number 2. So dice here will be different to the variable dice in our first problem, but it's set up just the same as being the sum of die 1 and die 2. And this time I've chosen to display it in a histogram. If you do this, then you can see, you can go back to the spreadsheet. If you do a Control and then R, that command does a recalculate on the spreadsheet. So back to 2.2 here, and you can see that 7 this time is not our modal group. Okay, more than likely it will be. And it is on this occasion. Okay. Just one other thing I'd like to show, and I will insert, actually I'll jump out of it. I will insert a new problem again. Insert problem, so I don't get my variables mixed over. And let's throw in a calculator. We've looked at dice. Let's go now to coins. I'm going to use the random binomial generator here. And let's say I run the rand bin command, say with 2, 0.5. What this is indicating is we're doing 2 Bernoulli trials where the success on any individual trial is 0.5. So this, for example, could be simulating how many heads I get in a game of 2-up. So I'm throwing 2 coins, and on each individual coin, the possibility of a head is 0.5. Okay. Now you can consider what would be the most frequent, least frequent there. I'm just going to compare that experimental probability quickly to the theoretical probability. There is a command in the probability distributions. If I go to normal PDF, so I'm looking at the probability density function. So 2 trials, each with a 0.5 probability of success. Let's say I wanted 2 heads. What's the probability of that? You already knew it. It was 0.5 by 0.5, in other words, 1/4. If that's the exact theoretical value, if instead I run that command without the 2, what it provides is the various probabilities for all possible outcomes. That is 0 heads, 1 head, and 2 heads. Of course, the sum of that is 1. But we're not doing theoretical. We want to do simulations of empirical probability. Let's bump this up. Let's say we've got 1,000 coins. And you're probably expecting that a modal figure there might be about 500. Let's do this, say, 1,000 times. So the first 1,000 is referring to the number of Bernoulli trials in the experiment, and the second 1,000 is the number of times we repeat that experiment. And there are our values, and as expected, a lot of them are sitting around the 500 mark. Let's store that to coins, and let's get a picture again. Control document. There are a number of ways of adding new applications in Inspire. You can see a few times now. This is my favorite. I go control and then document, which highlights this plus page. I know a lot of people like going back to the house here, the home. I see that as going backwards. I see that as kind of going back out of your document, whereas in my view, this is adding it within as we're going along. There are also a couple more examples here too, a couple more applications that aren't available through the house approach. Okay, so data and stats. Whoa, there's our 1,000 experimental results there for coins. And there we have them. And I'm going to change it this time to a histogram, menu plot type histogram. Okay. I would like to interrogate this a little more, zoom in on it, and I'm going to change the properties of that histogram in the bin settings. Yes, I want to continue with equal bin width, but I'm going to make it, instead of 1, I'm just going to make it, instead of 10, I'll make it 1. Well, okay, that worked, but of course it's pushed my scale down back into the menu, window zoom. Zoom data is a very useful command, which sets up our window in response to the data. And there we have it. Now, people might look at that and think, I reckon that looks like a normal distribution. Well, actually it's not. It certainly does look like it, But it's not a normal probability density function for the very reason that a normal PDF is continuous data, whereas, as you're well aware here, we're dealing with discrete data. But it kind of does fit to it. And let's have a look at how closely. If I go back in here and analyze our data, I can select this handy option down here, number 9, show normal PDF. So it looks at our data and wacko, that looks pretty close to our normal bell curve here. You can see that we have a mean of 500.6, standard deviation for our sample of 15.9. It's automatically multiplied by 1,000, otherwise we wouldn't see it. I think that's very cool. And I'm just going to hide that now before showing you my very last trick. So we'll hide that one. Another one we can do in the plot types, you've seen dot plot, box, oh, we haven't done box plot. You've seen dot plot and histogram. How about plot type normal probability plot? I think this is very cool. What it's done is it's taken my data and aligned them to their anticipated z-scores. You can see here our z-score formula. The individual score minus the mean divided by the standard deviation, and it's pretty close, particularly through the center here. I think that's a pretty cool way to start getting into our simulations. But don't worry, we've got more to come. I'm going to swap across now to Frank, who's going to look at one of my favorite problems, and this is one where theoretically it may be difficult to convince people, but if you launch into gathering some data by simulation, and Frank, you've got the control there. If you look at gathering some data by simulation, that can be more convincing for students. And there it is. You know it. You recognise it. The Monty Hall problem.
Oh, thank you, Brian, and good evening, everyone. Yes, I'll be looking at a classical problem, and all the work that Brian has been doing is relevant to what I'll be doing as well. So if you want to follow up on this, there is a student activity which is not on the TI Australia website yet because I've only just finished writing it, but I got so carried away that I actually decided to write it down on paper with student questions, the TSN file with the simulation, and teacher notes, which includes how to set up the basic simulation. Okay, so let's have a look at the problem. So it involves a game show with 3 doors. A prize is hidden behind one of the doors, no prize behind the other 2 doors. The contestant initially chooses a door. The host then opens a door not chosen by the contestant to reveal that there is no prize behind the door that the host has opened. The contestant is then invited to either stay with the initial choice or to switch doors. So the question is, to maximise the probability of winning the prize, should the contestant switch their choice of door or stay with their initial choice, or does it make no difference whether they stay or they switch? Now, a common hypothesis is that it makes no difference whether the contestant swaps or not. The reason being that, according to the hypothesis, once the host has opened a door, there are 2 doors remaining. There is an equal chance that the prize is behind either one of the 2 remaining doors. Well, that sounds plausible, but is it correct? Well, by carrying out the simulation, we can find out. So, in setting up the simulation, there are some assumptions that we have to make. So the assumption is that the door with the prize is labelled door 1, and the doors with no prize are labelled doors 2 and 3. These are not necessarily doors the first, second and third door from left to right. These are just labels, door 1 for the one with the prize, door 2 and 3 for the other two. If a contestant's initial choice is door 1, the host makes a random choice between doors 2 and 3 to be open. If the contestant's initial choice is door 2, the host opens door 3 and vice versa. So the host never reveals the prize and never opens the door chosen by the contestant. Okay, so setting up the simulation. So this simulation has been set up in a spreadsheet, a bit like what Brian did, except that some of the formulas are a bit different. So let's go to the spreadsheet. In column A, that's the initial door, the door chosen by the contestant. So we're simulating that by up in the top here, using that random int command. You can see down the bottom in the entry line where what we've entered up there. So because it's up the top of the spreadsheet, that will apply to the entire column. So we're choosing random integer from 1 to 3, and we're going to do 100 of them. The reason for doing 100 is that it then makes it easy to see the proportion. So, for example, if they get 34 wins or 50 wins, then it's easy to work out mentally 50 out of 100. So when we input that, we get the 100 random integers between 1 and 3 populating column A. Now, column B is the host door, the door opened by the host. Now, here, the formula we've used is an if command. So, in cell B1, if the contestant chose door 1, the host will randomly choose between 2 and 3. That's why it's random integer 2, 3. Otherwise, so the if command, it's got an expression, then the result if it's true, and the result if it's false. So if that's false, then, in other words, if A1 wasn't equal to 1, if the contestant didn't initially choose door 1, then you have another if command if that's false. If the initial choice was door 2, the host will open door 3. Otherwise, the host will open door 2. So that's the logic behind that command. All right. And in row C, the outcome if they stay with their initial choice. So that's another if. If A1 equals 1, in other words, if the contestant initially chose 1, then it's a win, otherwise it's a loss. Now the switch command. So in the switch, because 2 plus 3 equals 5, if A1 plus B1 equals 5, it means the only other choice left for the contestant when they switch is to choose door 1, in which case they win. So that's the logic behind that command. If the input in A1 plus B1 equals 5, then the switching results in selection of door 1, so they win, otherwise they lose. Okay, so that's only been entered into those 3 top cells. So how do we fill down to 100? So you can just click the first cell, B1, and then hold down the Shift key and arrow across to multi-select. Then you can get the context menu. The context menu is either a control menu on the handheld or a right mouse click on the software, and there's a command fill, and you just arrow down till you get to 100, press enter, and you fill down automatically. Now, when you fill down, because in the initial formula I only used relative cell references like A1 and B1, then when you fill down, that relative cell reference gets updated. So A1 gets updated to A2 and A3 and A4 and so on. All right, so that's basically what's running the simulation. Over here, I've counted the number of wins if I stay. So the command there is the count if command. So count if the stay column equals win. So every time in the stay column it sees win, it counts it. And we do the same down here for the switch column. Count if switch is a win. So once I've got that set up, I can do the same sort of thing that Brian did, and I can add, so control doc. I also prefer control doc. I can do data and statistics, and I see a whole lot of stuff here. I can press the tab key or click down the bottom there, and I can select stay, and it shows the number of wins and the number of losses if I stay. If I want to also show the switch, the easiest way of doing that is to go down the bottom here, and then the context menu, control menu, or the right mouse click, and add an X variable, choose switch, and it shows outcomes for stay and wins for the stay strategy and the switching strategy. I can, of course, change that to a bar chart just with the context menu, or going to the main menu, and then I can just hover over it and see what the percentages are. And if I go back to the spreadsheet and do as Brian said, Control R, then it recalculates, and I've got a different 100. So this time the proportions are slightly different. But what I can see is that it's certainly not 50-50. All right, now what I'm particularly interested in, though, is what happens if I repeat the trials many times. What happens to the success fraction? So what I'm going to do is observe the changes in the success fraction, which is the number of favourable outcomes divided by the number of trials, by looking at the outcomes one at a time. So what happens as to the success fraction as I increase the number of trials? So I want to introduce the idea of long-run proportion. So all I've done is I've done a few tweaks on the spreadsheet. So I start with the basic spreadsheet, and then I just add different embellishments, such as a couple of sliders that control things. So, for example, one of the embellishments is that rather than if I want to control the resetting of the recalculating from the data and statistics page, then I can do that with a slider by just adding, under my random integer, I can multiply by the value of the slider and divide by the value of the slider, which effectively is only multiplying by 1. However, as soon as the formula detects that something has changed, it will automatically recalculate. So that's a way of bluffing us into recalculating remotely, if you like. Okay, so here I've got no data to start with. Now, this time, I've set it up so that I can read one trial at a time. So I can see that as I'm read through my list, I can see that being populated. I can see more and more trials appearing. But what I'm interested in are the proportions. Looking one trial, so what's happening to the success fraction as I increase the number of trials? So I start here. I start with 0 and 1, the proportions of winning and losing. So the orange is success if I stay, and the blue is if I switch. Okay, so I can see what's happening as I increase, and I can automate that, so I can get the context menu and animate, and it automatically starts reading down the spreadsheet and working out the proportion just in an additional column that I've added to the spreadsheet. And one of the things that we see is that even though it's sort of a bit bumpy, that it does seem to be converging to this line. Now, this line is 2/3 for the switch and 1/3 for the stay, which is interesting. Okay, so students can take a look at that and see that even though there is variation from trial to trial, in the long run, it looks as though it is converging to a value. And in fact, this red line here, let's try the red line, I'll just press. The red line is in fact the mean of all of those success fractions, and we see that the red and the green are almost identical. Now, from this slider, I'm recalculating. I can recalculate from this slider, and we see, so that's for a different 100 trials, and it is different. But interestingly, even though the pattern looks quite different, in these cases, in the long run, it's also converging toward 1/3 and 2/3. And again, so with 100 trials, even though we get quite a bit of variation, invariably we get convergence towards 1/3 and 2/3. So it looks as though there was something wrong with that initial hypothesis. Okay, so if I want to look at even longer term proportion, what I can do is, instead of just looking at 100 trials, I can capture those. Every time I recalculate, I can capture that into another spreadsheet. So I've got the same old spreadsheet that I showed at the outset, and in this other spreadsheet, I'm using the capture command. So I capture the wins if I stay. The 1 just means that it does it automatically. And this CH, that's just a random number. The reason that you always, that with probability you should add a random number to the capture is that if you get successive results that are the same, it will only capture them once. But if you have this random number added to the capture command, then it detects that something has changed and it will capture them even if the value is the same as it was previously. So if you get 30 wins twice in a row, it will record twice. Without that CH, which is just a random integer, a random number that's hidden somewhere in the spreadsheet, it would only capture it once if you get repeated results. Okay, so every time I increase the value of n, I recalculate and it adds another 100 trials. So that shows the average proportion for 100 trials. That's what this is showing, and that's for another 100 and another 100 and so on. So the red is the mean of all of those trials. So this time we're up to, so for 20 times 100, so that's for 2,000 trials. And we can see that what's been happening is that the capture has been capturing all of those recalculations, and it's populated that spreadsheet. And we can see that with 100 trials, even though it moves around quite a bit, as I increase the number, we see that the average of all of those is almost exactly 2/3, 1/3, which is, so the green and the red are almost identical. All right, and we could do even more aggregation, and this is showing similar sort of thing, except this time it's just done on a magnified scale. So this is like if I was looking at it through a magnifying glass, because I've just expanded the vertical scale. And we can see that it doesn't matter how many simulations you do, we invariably get convergence towards 1/3 for the stay and 2/3 for the switch. So the conclusion is that in the long run, the switch strategy results in about 2/3 winning 2/3 of the time, and the stay 1/3. So why? So hopefully students begin to see that the host didn't choose that door at random. It depended on the contestant's initial choice and the location of the prize. So after the host had opened the door, there was a reduced sample space. So the contestant could then make a choice given the new information. So it's conditional probability. And in the worksheet, I actually do guide students through Bayes' theorem as an extension, so that if you want to do this with Year 11 students, you don't have to do the bit on Bayes' theorem. If you want to do the activity, you can leave that out. But it leads them through the assumptions, and it basically guides them into doing the calculation. And the conclusion is that, yes, indeed, the theoretical probability confirms the 1/3 and the 2/3 for the stay and switch strategy. And I think my time's up. So keep a lookout for the activity, which hopefully will be on the education.ti.com/AUS site soon. So that's all from me. So thank you, and I'll hand over to James.
Thanks, Frank. Classic problem. I really enjoy doing that one there. I also wrote in the comments there that a lot of these activities would translate very well into the investigations requirement that's in the revised study design as well. I also believe that students should initially start off by doing the physical experiments, and then in response to that natural feeling of, hey, but I need lots more data, that's then bringing in the power of electronic simulations. So thank you, Frank. I can see James, that you're set to go there, and James has another very interesting example for us here on sample mean distribution.
Hi there, everyone. In this section of the webinar, we'll be looking at one idea in which we could engage with simulation in the newly revised Unit 1-2 Specialist Maths course. In particular, as Brian said there, I'm using simulation to investigate the sample mean distribution. So the following is just an excerpt from the newly revised study design. Relates to the mathematical investigations. And as part of this excerpt, I think it's worthwhile noting the references to tabular and graphical representation of sample means, measures of center and spreads of the distribution, and in particular, exploring what the effects of sample size and the number of samples have on the distribution and its statistical measures. And this simulation and empirical work can form the solid foundations of understanding for the ideas that are explored in the Unit 3-4 Specialist Maths course. So the data we'll be looking at tonight is the maximum temperatures recorded in Melbourne over the summer months from 1970 to 2021, so quite a wide-ranging. And this is taken straight from the Bureau of Meteorology. Now, some observations over this time period are missing for whatever reason, perhaps due to replacing equipment or malfunctioning equipment. So we don't have the full data set, but we can perform some sampling to get a sense of the true average maximum temperature over a Melbourne summer over a long period of time there. Now, the data itself is quite a lot of data points here. And they're just copy and pasted straight from an Excel spreadsheet that's taken straight from the Bureau website, which is really handy feature of the Inspire. So this spreadsheet is the same as your Excel spreadsheet. Now, I've called the data D1970 to 2021. We're not allowed to have spaces in our names. So to get around that, we can put in some underscores where we would like to have a space there. And we also can't begin the name of a variable with a number. So we have to begin it with a letter. So I've just sort of referred to this as the data from 1970 to 2021 there. Now, before we jump into the heavy stuff, it's probably just worthwhile noting a few inbuilt commands to help us with the simulation in this aspect. So firstly, if we just want to calculate the mean of something, we can utilize the mean command. And so we do need to find the mean of a list. Now, depending on what we call the data and what you may decide to call the data yourself or your students may call it, it may be a bit tedious to keep on typing something like this in. So whatever it's defined, we can press the var button to bring up the data that we do define. And this could be defined in a calculator page or a spreadsheet, as I have on the previous page there. So that's just a nice shortcut to, again, so we don't have to type it in every single time. We do want to perform some random sampling. So we can utilize the randsamp command. So the way this works is we can generate a random sample of a specified number of objects. So here I'm asking for 5 numbers from my data set. Now, by default, it's sampling with replacements. So if we'd like to sample without replacements, we can put a (1) at the very end here. So in this case here, I'm picking 5 objects from my list, or 5 temperatures, without replacement there. Now, as part of this investigation, we would like to calculate a sample mean. So this is where we can begin to combine a few commands. So here we're taking the mean of a random sample, and that's just our lovely sample mean there. Now, we'd also like to generate quite a few sample means. Now, to do that effectively, we can use the sequence commands, SEQ or SEC. So what this is doing is it's generating a sequence of sample means. And we're going to use just a dummy variable k in this case here. And we're going to say it's going to generate, start from 1 sample mean and work our way up to 3 sample means there. Okay, so in our list, we've got 3 randomly generated sample means. It may look a little bit scary when we combine commands. So it might be a little bit best to start from the inside working out. In this case here, starting with a random sample, then finding the mean of that, and then just doing that a few times with the sequence command there. So for our simulation, just to begin with, we're going to find the sample mean of 5 samples and do that 200 times. So first up, we can start in a list and spreadsheets page. And we first need to call our sample mean something. Now, just to keep it in line with what I defined earlier on, I'm just going to start with SM for sample mean. And I'm just going to put an underscore to make the cats think it's a space and go from 1970 to 2021. In the cell below, we need to enter in our command. So as before, we want to generate quite a few sample means. So we can begin with the sequence commands. So we're going to generate a sequence of some means of our data set. So the data we want to bring in, random sample name. The data we want to bring in there is those that data we had on the earlier spreadsheet page. So we can refer to that using the var button. And there's our data. So we want to sample from this data set. Now we're going to pick 5 of those, and we're going to sample without replacement. So just a column 1. After that. Now from here, we want to put in our dummy variable k and tell the Inspire that we're going to go from 1 sample to 200. So there we're going to get 200 sample means that have been randomly generated there. Now, as part of this, and sort of referencing what was said in the study design, we do kind of want to see the graphical and data as we do some simulation. So just for the time being, I'm going to open up a bit of a split screen here. So as Brian and Frank demonstrated earlier on, we can insert a new page. So insert page. And I'm going to do something a little bit different. So before I select my data and stats for the time being, I'm actually just going to change how my page looks. Just changing my page layout. And I'm going to select option 3 here, just so I can have the data and stats. Down the bottom, I'll put in a notes page, which I'll come back to in a tick. So as Brian demonstrated earlier on, there's our data set that we just generated. And select our data for the sample means. There's our lovely dot plot with the 200 sample means. And we're sort of starting to sort of see a little bit of a bell curve there with a bit of a wink to where this might be leading. But as we sort of said with reference to the study design, we do want to sort of understand what the mean and standard deviation are of our distribution. So what we can do is back in our list and spreadsheets page from earlier on, we can perform a one variable statistics calculation which will spit out all of the key statistical measures of our data set. So if we've not seen this before, we can go to menu, statistics, stat calculations, and just a one variable stats. Now, the list that we want to select from is our sample mean information. And at the moment, this is all fine. It's just going to tell us. See there? It's perfectly fine. And so what this is telling us is that our mean of the data set is about 25.86. We have some other nice stuff, but what we do care about is the mean and our sample standard deviation. Down below it is the population standard deviation, but for us, we'll be happy enough with the sample standard deviation. Now, it would be nice to get that side by side rather than having to flick in between our pages there. And so that's the reason for this notes page just down the bottom here. So all the information that we just generated is stored within the Inspire. So to get that displaying, we can insert a math box by pressing Control M. Then to get that sample, to get those mean that we just generated, we press the var button. We've got all of our statistical measures generated there. And as we can see here, there's our lovely X bar, that mean that we just generated, which is 25.86, same as before. Side by side, and insert another math box to also display the sample standard deviation. As also as part of what the study design sort of alluded to before, we also might want to consider how does the sample sizes and the number of samples affect our distribution and our key measures here. So what we can do is insert a slider, which is what Frank was playing with earlier on. So to do that, we firstly just want to click into our data and stats page to make sure that we're actually operating in it. And then by pressing menu, actions, we can insert a slider. So for the sample size, I might call it N. Now before we had a sample size of 5, so I might just start that there. And we might decide to take it up to, say, 100. And we might want to go in increments of 5. And to make life just a little bit easier, select the minimized button so that now our slider is just a nice clicker for us to use. Likewise, we can set another slider for the number of samples that we decide to choose. We might call that one NS. And we started with 200 with our first demonstration there. And we may decide to go up to 1,000. And perhaps we want to go in increments of 100 at a time. Likewise, selecting that minimize button there. At the moment, these guys aren't doing anything because they're not actually linked to the data. So what we can do is jump on back to the data set that we played around with. And now we're just going to tell the Inspire that actually, instead of a number of samples being 5, sample size being 5, we want the sample size to be n. Likewise, in 200 samples, I'm going to take ns samples. Now, the Inspire will ask whether n is a column or a variable. So we just want to reassure the Inspire that actually n is a variable there. Now, this is where the power of the Inspire will be on display here, because now when we play with the sliders, you see dynamically that the distribution is updating, but also if you keep your eye down the bottom of the screen there, both the mean and the the sample standard deviation are also updating live. So rather than having to flick between our screens from this to the spreadsheet from before, it can just be all on the one page for us. So that's, and also likewise, number of samples there. If for whatever reason we may decide to change these dot plots to a histogram, which Brian demonstrated earlier on in the same sort of fashion, we may need to also change the size of the windows. Likewise, that can be done via menu, window, and we can go zoom data. But in terms of the actual investigation from here, we could potentially fix the number of samples, let's say maybe at 500, and then get the kids to consider what is the effect, how does varying the sample size affect the shape of the distribution and the mean and standard deviation. They can sort of have a nice sort of empirical play around with it. And likewise, we could potentially fix the sample size and have them consider how does the number of samples affect the distribution, and likewise even compare those two comparisons is worthwhile there. And I guess that's really about all from me. So Brian, I'll throw it back to you. And likewise, if people have any questions, feel free to put them in the chat.
Terrific. Thanks. Thanks there, James. And I'm particularly keen to see that you actually referenced the revised study design there, which I dare say I really should have at the start to see where all this is actually coming from. That, of course, should be the prime document that people are referring to. And you've, as I said, addressed one of the specific things there with the distribution of a sample mean, something that teachers may have been wondering about. A couple of questions that came through in the chat there. First of all, I might actually jump back to show the first one. Someone was asking about transfer of files. So they're seeing that we've got the we use the emulator. How can we transfer files, say that they've downloaded from the website or taken elsewhere off the internet? So I'll just share my screen here onto student calculators and the like. So through the emulator, if you look in the documents toolbox here, you've got this one here, Content Explorer. So what I often do is just do a drag and drop, and so here you can see actually the file set up on my computer. So I can actually drag files out of here if I find a TNS or TI-nspire file, and if I connect in a handheld, which I haven't done at the moment, but it would appear down here as well, and likewise you can see the file system for that. So you can generally just do a drag and drop. The other way, of course, is to just open up another window on your computer. I'm using a Windows-based computer here, and drag the file that you've taken from, say, the TI website or elsewhere, and drop it into the handheld. I find that the easiest. There is also another range of software for connecting without using the emulator. So I'll close this out now. Oh, other questions that were there, by the way, was Is the session being recorded? The answer is yes. Two places to find it is on the TI Australia website itself, in the archive of past webinars, or the other one is on our YouTube channel. The links to both of those, if you look back through the chat history, you can find them. And if you just click on those links, it'll automatically open in your browser now. So thank you, Frank, and thank you, James. I think this has turned into a pretty good and comprehensive session that we've organised for this evening. If if the participants do have any last-minute questions or comments to us panelists, now is your opportunity to type that in. Can I remind you to stay tuned? There is more coming in what's proving to be a very popular webinar series for the the 2023 VCE with revised study design for next year. You can see there some additional topics for not just maths methods, but also the general maths and the specialist maths. So thank you to my co-presenters this evening. And I can see lots of positive comments and thank yous coming through in the chat there. Lovely to see that. So stay tuned for more in the program. As I said, keep an eye on your inbox for the newsletter. Hopefully you're subscribed to, and if you're not, just go to the Texas Instruments Australia website and see what's going on there. All the very best. Enjoy the remainder of your evening.
Bye, everyone.